Sure, I'll break down the document section by section, diving deeper into each part. Section 1. What is a dead leg? A dead leg in a water distribution system is a part of the pipe where water flow is minimal or non-existent. This can happen when a pipe is connected to a point of use, like a tap or equipment that's rarely used. A pipe has a dead end where water can't flow out continuously. These areas are problematic because water stagnates, creating an ideal environment for microbial growth, like bacteria and fungi. Biofilms, thin layers of bacteria, can form in the stagnant areas, making it harder to clean and sanitize the pipes. In pharmaceutical water systems, where cleanliness is crucial, these stagnant zones are a significant risk to the integrity of the entire system. Section 2. Why dead legs are problematic. Microbial growth and contamination. The stagnant water in dead legs serves as a breeding ground for microorganisms. These organisms can form biofilms, which are difficult to remove and can lead to system contamination. This could affect the quality of pharmaceutical products. Cleaning and sterilization issues. Dead legs are hard to clean because the water doesn't circulate. This makes it challenging to maintain the system's sterility, especially during CIP, clean in place, and SIP, sterilize in place processes. A dead leg in pharmaceutical water systems is, therefore, a worst-case scenario for ensuring safe, clean water. Section 3. Industry Guidelines and Standards. The document outlines different guidelines and standards that define the length of dead legs and how to manage them. 1. LD ratio, length to diameter ratio. This is a key measurement used to assess the risk posed by dead legs. It is calculated by dividing the length of the dead leg by the diameter of the pipe, LD. To minimize the risk of stagnation and microbial contamination, most standards recommend keeping the LD ratio less than 2, meaning the length should be no more than twice the diameter of the pipe. FDA Guide 1993, FDA regulations for high-purity water systems mention a 6D rule, meaning the dead leg should not be longer than 6 times the diameter of the pipe for hot circulating water systems. For cold water systems, not self-sanitizing, the recommendation is to eliminate dead legs altogether or use special sanitizing methods. 3. WHO and SME standards. WHO TRS 12 and ASME BPE 2016 recommend stricter rules for dead legs, with the maximum LD ratio being 1.5D for critical systems, which are more sensitive to contamination. Section 4. Prevention and Management of Dead Legs. In this section, the document emphasizes how to prevent and manage dead legs. 1. Design. The most effective way to manage dead legs is to design systems that avoid them altogether. If possible, pipes should be designed with no dead ends and continuous flow. The use of low-profile or flangeless fittings can reduce the risk of creating dead legs. 2. Sanitizing procedures. When dead legs cannot be avoided, regular flushing or sanitization is recommended to prevent microbial growth. In systems where dead legs are inevitable, like in certain legacy systems, special sanitizing procedures or periodic flushing may be implemented to control the microbial risk. Section 5. Conclusion. This section summarizes the key points about dead legs. The goal should always be to minimize or eliminate dead legs in the design phase to prevent microbial contamination and improve system cleanliness. The document reiterates that a LD ratio of 2 or less is considered ideal for new systems to avoid dead leg formation. For legacy systems, older systems that might not meet the modern standards, it is still important to recognize the dead leg areas and take steps to manage them, such as by frequent cleaning or sanitizing. The LD ratio is a key factor in assessing the potential for dead legs. Keeping it low helps in ensuring the system remains clean and free from microbial contamination.